Thanks, Risa. Thank you very much for the invitation. I'm going to give a very short mini course on these topics. I will start with motivic periods and we'll see how far we get. Now, the theory of motivic periods uses the work of a great many people, but the formalism I'm going to describe is something I developed about a decade ago. At that time, I made some mistakes, not mathematical mistakes, but I kind of regret the way I presented things. I didn't give many talks on it, and the way it's written in the literature is very dry and technical, and that's sort of my own sort of character failings, which account for that. And so recently, since this has been being used a lot by the physics community, I thought it's a good time to sort of change the narrative and explain things the way I should have done, in a way that's really intuitive and natural. So I gave a mini course in Trieste at the end of summer. There will be typewritten notes, which are very detailed, and everything I say and much more will be in those notes. And I hope that you will refer to them if you want, and once they are available. So for physicists, physicists are using this a lot to great effect. I think for you, the value of this is to revisit the foundations again and go into a bit more detail. And also I'd like to highlight some subtleties where there's quite a bit of confusion. For mathematicians, this is a difficult one because you are going to think that this is completely formal. And at no point will you see that anything particularly interesting has happened. This is completely wrong because the ideas are I think the framework is right, the ideas are natural, and it's deceptively simple. So my answer to you is either work out an example, and it's very surprising that this really gives something highly non-trivial, or talk to a physicist, and they will put you out of your misery. Okay, so I've spoken too much. Let's start with periods. So all lectures on periods start the same way. So classical periods are numbers. They're just numbers, certain type of numbers, and they form a ring, which we call P for periods, and it's a subring of the complex numbers. I'm sure many of you have seen this before, so I'll go quite quickly. Examples of periods include Q bar, algebraic numbers, our favorite constants like pi, theta 3 we'll discuss quite a bit. Generally, we expect values, positive values of zeta and L functions. If you're a number theorist, that's interesting. This is conjectural. Part of Deligne and Beilinsen's conjectures. And another family of examples are convergent integrals of the form I P so here sigma is the region given by, let's say, FR positive, where F1, FR, and P and Q for that matter, are polynomials with rational coefficients in n variables. Yeah, you can show that you can reduce that all periods can be written in this form. And I, sorry, this has to be real, and square root of -1, I think. So no, you need to take real and imaginary parts of these. But with that, I think that covers everything. Okay, so that's a classical, so-called classical periods. Because classical means just that which the speaker does not want to talk about. Next up are families of periods. So now so these are numbers, now we want functions. So these are going to be multi-valued functions. And some of our favorite examples include log of z, function of z. Otherwise, we very quickly encounter the dilogarithm. And for, I guess, half of this audience, very important class of functions are Feynman integrals. But in some fixed spacetime dimensions. So let me just say let's take even dimensions just to be simple, but you could take odd dimensions, it's fine. So then we have integrals of the form. So this family of integrals I can be promoted to a function by the same things before. Let me just be a little bit brief. Sigma p over q dxn. But now sigma p and q could depend on extra variables. So let me just say now we allow p, q, and the fi to be polynomials not only in x1, xn, but also some other variables, z1 up to zr, let's say. And so these integrals, if they converge, are going to be functions of these unintegrated parameters. Okay, so far so classical, so traditional. The first class is we understand quite a lot what to do with. This family, again, we understand quite well, but it's less developed. The third family I want to discuss are what we like to call Mellin periods. And here the theory is very much in its infancy. The work here is on Mellin periods is joint with Clément Dupont, Mathieu Tapuskovich, and Javier Frezan. We'll be writing a paper on this very shortly. The examples include the beta function, beta s comma t, as a function of s and t. Things like hypergeometric functions. And in general, we're going to look at an integral SR of the form, again, let me be slightly cartoonish about this, F1 to the S1, FR to the SR of omega. This sigma could be, say, this domain, if you like. Omega could be exactly this integrand. I don't want to write it out again. Oh, sorry, this is F. This is terrible. This F is not the same F. Let me change that immediately. The G1 up to GR. So here, G1 up to GR are some new polynomials. And so this is a R-fold Mellin transform. Again, here, everything inside is algebraic. Omega, for example, is a rational function. Sigma is defined by polynomial inequalities. So that's what we have in mind when we talk about Mellin integrals. And Feynman integrals now in dimensional regularization are also an example. In dim reg, so this is in 4 minus 2 epsilon dimensions. So we're going to think of epsilon will be a Mellin parameter, a Mellin exponent. Okay, so there's a version of this in this setting where we now have parameters as well. We can have some unintegrated variables in this integral as well. That's totally fine. And we can go more general still, so this is something for the future. We can keep going. We can even cook up integrals. Now, I'm really making it up now, but we can put some solutions to some random looking algebraic differential equation, like a hypergeometric function, and we can put any old omega and sigma here. And we can view this as a function of things like A, B, C, and also as a function of variables which are internal to sigma and omega. There's a vast generalization, which I think we are going to have to affront at some point. Okay, so go back to the very first example of algebraic numbers, and Galois told us that there is a huge symmetry group G, which we call Gal Q bar over Q, which acts on all algebraic numbers. So algebraic numbers aren't just numbers, they're some things which dance around in some incredibly complicated way, which respects all possible algebraic relations between them. For example, when we act on the positive square root of 2 by an element of this group, it becomes plus or minus, depending on the element in the group, the square root of 2. Okay. Conjecture. There exist generalized Galois groups of some kind acting on all the above versions of periods. So instead of what are typically here sort of discrete groups, here we get the group, finite group of order 2. Typically, when we have, this is called a Motivic Galois group, or a Motivic Galois group, when it acts on a period, or one of these variants, it's going to act as a matrix group. So let's do a very basic example, because I'll use it again. An element in this Motivic Galois group could conjecturally act on zeta 3. And what it's going to do is it's going to scale zeta 3 by some rational number. And it can translate zeta 3 by any other rational number. This is how the Galois group is going to act. Oh, this one can't move. Okay, so you don't want me to try and break it.
It's already.
It's just okay. Okay, so this is totally surprising that it's possible to do this at all. And so I claim that these groups should respect all possible algebraic relations between periods. And as we know, these are incredibly rich and structured things. We know a plethora of algebraic identities. It's very surprising that there exists any element at all that acts non-trivially on them. In other words, that you have the latitude to change the solutions to these equations in a non-trivial way. It's surprising. And so what are Motivic periods? This is the framework I want to discuss. It's a framework in which, It's a theory in which everything works. Theory to make everything work unconditionally. With no assumptions, no conjectures. And as the physicists know very well, that you can really compute in this theory, and you can produce predictions. You do computations. And you can discover new structures. So we'll see, hopefully, how to differentiate with respect to a number. We can differentiate with respect to zeta of 3. And we can discover new symmetries which were not previously apparent. Okay, so now let me straight away tell you what the key idea is. There's one key idea in this whole business. If you just take away one fact, it's this one. So when we think about periods, don't think about just one integral. The wrong thing to do. We're going to replace individual period integrals with matrices of period integrals. That's the key idea. And as we'll see, in periods, or in all these settings, naturally arise as part of a period of other like-minded period integrals. And they talk to each other. It's a very bad idea to just pull one out and consider it in isolation. And this is what Galois taught us. He says, don't think of square root of 2. It actually doesn't make any sense to think of square root of 2. You need to think about square root of 2 and minus the square root of 2, because they are the two solutions to the equation x squared equals 2. So we're doing the same thing here. So here's an example, zeta n. I should show you why it's a period, first of all. So apologies to those of you who've seen this a million times. So here's zeta, Riemann zeta of n as a period integral actually an iterated integral for those who know. So this is, because of this integral representation, it is a period. And so what we do is we take the number zeta of 3, and as I will explain how to do, we replace it we replace the number zeta of 3 with a matrix. The matrix is this one, 1 zeta 3 0 2 pi I cubed. And I'll spend the first half of the talk explaining why it looks like that. So basically, what a Motivic period will be a matrix like this, up to some choices of changing basis and so forth, plus some extra structures. You have a sort of liberty to include or not, plus a choice of a distinguished entry. The Motivic period will be basically a matrix of this type, plus the data of remembering that it's this number in this slot, which is the one we're interested in. Okay? So modulo sum equivalence. Modulo sum equivalence relation. Which is basically things like doing row and column operations, and identifying a period matrix as a sub-period matrix of a bigger matrix. Things like that. You're allowed to do things like that. So what are these extra structures? Well, it's a long story, but one of them is, let me put it here quickly. One of these extra structures is that this matrix can always be put in block upper triangular form. This follows from Deline's mixed Hodge theory. Okay. So I guess the first thing I need to do is to explain to you why periods naturally arise as entries of matrices of periods. Are there any questions while I in the boards? What are the blocks? What's the weight filtration? So the blocks correspond to the period matrices of the associated weight graded. Period matrices. So I'm going to start off now with X just to smooth. Okay, I want to give you the definitions as they are, without cheating or dumbing down. So there'll be some words here you might not know, but it doesn't matter, because in the cases we're interested in, it's something very concrete and elementary. But I think it's important to say the correct words. So this goes back really to Grothendieck. In fact, almost all of this really comes from the ideas of Grothendieck, to be honest. He defines what's called the algebraic de Rham cohomology of X. And the technical definition is it is the hypercohomology of X in the sheaf of Kähler differentials. Okay, so this uses quite a lot of words. I'm not going to explain. In practice, it's actually something very concrete. That doesn't mean it's easy to calculate. But the first simplification is that if X is affine, and we can pretty much always assume that in the world of periods, we can always reduce to that case, then it's something much simpler. De Rham cohomology of X is isomorphic to the cohomology of, I use a slightly non-standard notation here, it's cohomology of the global regular differential forms. So these are the global sections of the Kähler differentials. Okay, so concretely, what is this? This is a complex omega de Rham brackets X is the algebraic de Rham complex. And because we're in the affine case, it's this thing. Okay, so these are global regular n forms on X. These are global regular n plus 1 forms. And this is the usual differential. And so if you don't like those words, you can simply take Hn dx is simply closed regular n forms on X modulo exact regular n forms on X. If we were doing complex manifolds and we just worked with smooth forms, this would exactly be the definition of the usual de Rham cohomology. It's things which satisfy D is 0 modulo D of something. And this is just what the naive thing you might expect. You just replace smooth with algebraic. So you work everywhere with algebraic differential forms. And miraculously, in the affine case, that gives exactly what you want. In the non-affine case, it's not true. But this is something, therefore, should be very familiar. Now, to do integrals, we need domains of integration. So for that, we need singular homology, and we like to call it Betti homology. Right, so Hn Betti of x of c. The x of c is the complex points of this smooth variety. It's a complex manifold. I'll do some examples in just a moment. So Hn Betti xc is closed singular n chains modulo boundaries. These are linear combinations of maps from a simplex into complex points of our algebraic variety. So an arbitrary linear combination of finitely many such maps, such that all the boundaries glue together. And such a singular chain is called trivial if it is itself the boundary of some other chain. So then Grothendieck and Durand. Grothendieck-Durand theorem is that there is an integration map from the Durand cohomology gives an isomorphism to the dual of the Betti homology. What it does, it takes a differential form, a closed differential n form, and we do the obvious thing. We take a representative of a closed n chain, and we integrate the differential form over the chain. So every differential form can be viewed as a map from closed chains to numbers, and therefore it's in this dual. And the theorem is that this is an isomorphism. So the corollary of this, since the homology is something that's a purely topological invariant, we can use things like my Vietoris sequence and so forth. Very easy to compute this topologically. And we deduce, since we know that this homology is finite dimensional, then so too must be the Durand cohomology. Which is absolutely not obvious from the definition. It's really a deep fact. So what we do then, we can choose a basis, omega 1, omega d of our Durand cohomology. These are representatives for some closed regular n forms. And we can choose a basis of our homology. These are some closed chains. And we can form the period matrix relative to this choice of basis, Pij, the matrix P and its ijth entry will be the integral of omega j over sigma I. Okay, so what is the meaning of this matrix? Well, it's just this map, right? Just the map, this isomorphism integration, but written in a particular choice of basis. Sometimes I will just call P this map. H, N, T, X, answer Q, C. Called the period isomorphism. And in fact, all the period integrals we are interested in will always appear like this. And so already at this point, I hope I've convinced you that when you have a period integral, it naturally sits in some matrix. So let's do an example. Typically, when you do this, if you have a specific integral you're interested in, it's going to appear as in some absolutely gigantic matrix, which is full of junk. So there's the stuff you want, and there's a lot of garbage. And what you have to do is to sort of extract from this enormous period matrix the piece that you want. And that involves a machine, which I'm going to describe later. The example is slightly deceptive because it's too easy. Life is more complicated, as we know. But let me take X, a smooth elliptic curve. Over Q. So let me take a Weierstrass form like this. The concrete, so A, B, rational numbers. And I'm going to assume it's smooth, so the discriminant is non-zero. So as we all know, the de Rham cohomology of an elliptic curve has dimension 2, and it's spanned by two differential forms of the first and what are called first and second kind. So there's the holomorphic differential dx over y, and there's the differential of the second kind, x dx over y. So this form is actually on E minus 0, where we puncture the elliptic curve at its origin, at infinity, because it has a pole there. That's what's of the second kind. And then the Betti homology is a two-dimensional vector space spanned by the A and B cycles, called alpha and beta. So if I draw a picture, we have our elliptic curve. So on our elliptic curve, we have perhaps alpha that goes like this. See that? And then beta, alpha, beta. And then the period matrix, or a period matrix, would look like the data of these four integrals. If we do this correctly, we normalize things correctly, so I may not have done that, then Legendre tells us that the determinant is basically 2 pi I up to some constant, but if you normalize it correctly, you can make it actually 2 pi I. So like suitably normalized. Been a bit sloppy. But this period matrix depends on which choice of basis we take for the cohomology. Now, so if you've been paying attention, you will see I've done my speciality, which is I have immediately contradicted myself. I wrote something here on the board, and I've written something completely different. And I thought I'd just take a small time out to explain why that answer is not the same as this answer, and how to repair it. So let's go through the definition. What is the affine ring of elliptic curve? To be concrete, so it is Q of x, y, modulo the ideal generated by the defining equation. And as a module, as a vector space, if you like, it's Q of x, direct sum y Q of x. This has a basis given by x to the I, or x to the I times y. And what are the one forms? So this is what I called omega 0 of E earlier. Omega 1 of E is it's O of E dx, direct sum of E dy, modulo a relation which is the derivative of the equation. So if it's something like 2y dy minus 3x squared. Okay, and so you write down the Durand complex as a map from here to here, which is take a polynomial here and apply d of it. Okay, so x goes to d of x, y goes to d of y. And then we're asking for the co-kernel of that map. What are the elements here which are closed, they're automatically closed, but which are not in the image of differential, okay? So maybe I should write that actually. H1 Durand E equals omega 1 E mod, in this case, because there are no, it turns out that there are no two forms because of this relation. Anyway. Okay, so what does a one form look like? Well, every one form, have I made a mistake? Yeah? Oh, thank you very much. Yeah. E is the punctured elliptic curve. Thank you. Yes. Let me... Of course, so do we want to do the affine case? Thank you very much. It's very important. This equals E prime. Thank you. So this is what the Grothendieck theorem tells us, that this is the right thing to do. And so what is a one form here? Well, a one form, for example, the holomorphic one form should be representable in this. It should be f of something. Nice to write it 2f dx plus 2g dy. So Grothendieck tells us that every one form, every cohomology class on the elliptic curve, it should be something dx plus something dy. And this is why I've done something that's blatantly not of that form. What I wrote is the answer is a complete contradiction of the theorem I had previously stated, except for the fact that you can actually find f and g such that this is true. I know many of you are proficient in Macaulay and other packages. You can leave that as a great exercise to work out, and I will give you just f as a taster, and you can work out what g is. So f equals 27 b minus 18 ax over twice the discriminant y. I think that's correct. Delta is 4a cubed minus 27b squared. I leave you to work out what g is. Already for an elliptic curve, this Grothendieck theorem is quite interesting. Gosh. So now I'll quickly pass to relative cohomology. So the domain of integration sigma in our examples often has a boundary. It doesn't fit into this framework. So the boundary is typically contained in some subvariety y of x, an algebraic subvariety. And in this setting, we have to replace cohomology with relative cohomology. So again, I want to give you the definition because I don't want to cheat. I have y in x a divisor. Then we have the inclusion x minus y into x. Then I can define relative Ram cohomology to be the hypercohomology of x with coefficients in the pullback of the sheaf of Cayley differentials to the open, and then extension by 0. And concretely, it's something very concrete. It means essentially you're working with differential forms which vanish along y. I don't have time to go into further detail. But the homology, the relative homology, is something very straightforward. It's closed. It's the singular homology, if you like. If you're a topologist, you can just take the homology of the quotient. I'm low on time. That's probably the simplest definition you can take of the relative homology. And what that means, is that we allow change with boundaries. Oh, perfect. So code and chains with boundary contained in y of c. Modulo boundaries and chains contained in y. Slightly approximate, but it'll do. So this is the relative version. Okay, and then we have the same isomorphism, but variant of Grothendieck's theorem is that the relative cohomology x relative to y is isomorphic H relative Betti homology Q E. And so in this relative setting, we also get period matrices. The bottom line is that we can deal with integration domains with boundary, that's fine. And as I won't say, we can deal with all these other families of integrals we're talking about. We can find or develop cohomology theories in which everything I say has some kind of generalization. True. Okay, so Motivic periods. What do we do next? We replace a period integral, an individual integral, for some number So a number, let's call it P, given a sum integral, and we're going to replace it by something we call P superscript M, which is basically a matrix of periods plus a choice of entry corresponding to P. Modulo equivalence. The equivalence takes into account the fact that we were allowed to change basis in our period matrix, and we need to put in some equivalence relation in case we wanted to change basis. That's allowed. But also we may have chosen to change the algebraic variety x or y. We may have deleted a point as we did with the elliptic curve. We may do something else. We may do some blow-ups, and that will give us some equivalence on this side here. And so the framework will produce. So this is in a ring capital P of M. It's a period in a ring P, and the framework will give us a homomorphism from a ring of Motivic periods, I'm going to explain in a minute, to P, which takes our matrix and just picks out the entry that was selected as part of its data. This is called a period homomorphism. I'll explain in a minute how to do that, but first I'll state the result. So the claim is that there is, if you like, theorem, there is an unconditional Galois theory of the ring PM. I haven't defined PM, I'll do that in a minute, hopefully by the end of this lecture. And so what that means is that we have a group, huge group G acting on PM, where G is what is called a pro-algebraic group. So it's like it's a projective limit of finite dimensional matrix groups, subgroups of GLN, called the Durand-Motivic-Galois group. A possible definition of a Durand-Motivic-Galois group. There are others. And in this framework, all the theorems that you know from Galois theory are true. So here's an example. Let's get the example. Sorry. Okay, so my next task now is to try to set this up for you, define rigorously what PM is, so make this sort of heuristic rigorous, and explain to you what G is and how it acts. Okay, so this is part 2. Periods. Okay, so this will be a little bit dry, but I think it's worth doing because we know we're on solid ground. And it's actually very quite straightforward theory to work with. Definition. I'm going to take the absolute simplest possible setting that one can take in order to set this up. I'm going to consider an abelian category. This is a category where you have kernels and co-kernels. And all the usual properties. This is what's called a category of realizations. Don't worry about what that means. which is a category I'm going to call curly H. And the sort of de minimis category I can take is something very simple. It's going to be consist of objects M, where M is just a triple consisting of two vector spaces and an isomorphism. So MDR and MB are finite dimensional vector spaces over Q. Of course, we're thinking of cohomology of something. So MDR, we think of differential forms. MBETI, we think of something like chains. And CM is basically just the data of a period isomorphism. So in particular, these vector spaces had better have the same dimension. Okay, so I'm just formalizing what we did. Yeah? Yes. Yes. Well, I explained. So what this is perfectly fine. This is the right answer, but it doesn't quite fit with the algebraic Durand theorem I told you for an affine variety. And so the exercise was to bridge the gap and to write these indeed in the form that I said you could. If you want to do this like that, you can using hypercohomology, you can perfectly well recover the these on the nose, but it's more subtle than it looks. Is my point, I guess. And the point is, on an elliptic curve, you can't have your cake and eat it. You can't represent all the differential forms globally. I mean, you have to put poles somewhere, and that's just one of many subtleties that one encounters. It's kind of why I'm emphasizing the elliptic curve case and not the polylog setting that everyone's used to, because there are all these little things which don't quite generalize. I chose to emphasize that this time. Okay, so let's start with a period integral. So it's an integral of some differential form over some chain. And suppose we can interpret that differential form in that chain as some geometric situation. So omega is some form on some smooth variety X, sigma is some chain on X with some boundary in Y. So what does that mean? What's the meaning of that? This is the whole game. So HNXY is an object in this category. It's the triple HN Durand XY, HN, I'm going to write HN upper N, so this is the dual, so H upper N is the dual of homology. And then the period matrix. So this is an object of HQ. And so what does it mean to be a period of this object? Well, omega is thought of actually as a class in this cohomology group, and sigma is a class in relative homology group dual, which was just the homology. Okay, so we've taken our period, some number, and we interpret it as coming from the cohomology of something. Obviously, when you write the differential form, you mean a form on something. I mean, it's not just some symbol. It secretly encodes some geometric information. And then we put this into this category and we code the data like this. And then we define the Motivic version. The big word Motivic, but I kind of inherited it. Motivic period IM is some symbol. It's the data of this triple of vector spaces and comparison isomorphisms, plus choice of sigma and omega. In other words, what is this triple? This triple is just saying it's just a linear map from one vector space to another vector space. It's just an abstract way to represent a matrix. So this is just an abstract matrix up to changes of bases. And this defines a choice of entry in this matrix. This picks out a row and this picks out a column. So what are these symbols? What time did I'm very confused about what time I started. Oh, phew, okay. Whew. Oh, I've got an extra 15 minutes. Good, thank you very much. Nice now, okay. So what are these symbols? If I take a triple like this, these symbols are called matrix coefficients. So I take symbols M, sigma, omega, where M is an object of my category HQ, so it's two vector spaces and an isomorphism between their complexifications. Sigma is an element in the dual of the Betti vector space, and omega is an element in the Durand vector space. Okay, so think of it as some kind of abstraction of an integral. So we have these symbols and they satisfy relations. So the first relation is kind of obvious one. If we think of this as somehow the integral of omega over sigma, we know that integrals behave linearly with respect to integrands, so it should be linear in omega. In fact, it's linear also in sigma and omega. So we have M sigma 1. Let me just do base of sigma, and you can do omega yourself. Sigma 2 omega. So here, lambda 1 and lambda 2 in Q, and it's the same for omega. Now, the subtle thing, which looks like nothing, but it's actually the whole key to this business, and it's kind of confusing. So this is essentially the formalization of like a change of basic, sorry, change of what I'm looking for. Change of variables formula for integrals. So in this category M, I forgot to tell you what morphisms were. So what are the morphisms in this category? Let me write that over here. So a morphism in this category is basically the data of M Durand, N Durand, so linear, the linear map of two Q vector spaces. It's the data of a linear map between the Betti vector spaces. There's two linear maps between each of these vector spaces, such that it's compatible with the comparison maps, the isomorphisms. If I first apply phi and then go from n Durham to n Betti, that's the same thing as if I were to go from phi b dm. I've been a little bit sloppy here. You need to tensor with the complex numbers, but it's the obvious relations that these linear maps should be compatible with the comparison, the period isomorphisms. So that's what a morphism is in this category. And given any such morphism, then we get a relation which is Motivic period of M phi Betti transpose sigma omega is the same thing as n sigma phi Durham omega. So this is essentially the change of variables formula for integration. If I have an integral and I have a change of variables phi, I can transform the integrand, provided that I transform the domain of integration simultaneously. And what's subtle about this is that this map, phi Durham, goes in one direction from m to n, but phi Betti dual goes in the wrong direction. And that's what makes this subtle. For example, if you're, so any map, so what's confusing about this is any map always gives you relation between Motivic periods. So as an exercise to check you've understood the definition, you can look at the map from M to 0. Always have a map to the 0 object. And so convince yourself that that does not imply that all these symbols are 0. Conversely, there's a map from the 0 object into any other object. That gives relations, but those relations don't kill everything. In fact, you can see that they don't kill everything because there's a period map. Oh, I forgot to define PM, sorry. Let's scroll back. So what is PM? PM, ring of Motivic periods, is Q vector space generated by symbols, the Motivic integrals. I had it earlier, IM. Let me write it out again. Right. Square brackets. Omega, sigma omega, modulo the relations I described. Another great exercise is to retrieve algebraic numbers. It's a bit difficult, but it's written somewhere. Retrieve algebraic numbers contained in PM. This is the case n equals 0. X is a point. Oh, that's not, well, let me leave it at that. Okay, it's maybe a little bit more difficult then. Anyway, this is the Q vector space generated by these symbols. And it comes equipped with a period map. Comes with a period map per from Pm to the complex numbers, and what is the period of one of these matrix coefficients, it equals, well, what have we got? M is two vector spaces, a linear map, and we have two distinguished entries in each of these vector spaces. We can just put them all together. So we take our element omega, which is an M Durham, we apply the period map Cm, and that pushes it into M Betty. And then we have an element in the dual of Betty, so we can apply sigma. So we have M Ram tends to C, M Betty tends to C, and we have omega tends to 1 here, goes to Cm omega. Let me get rid of the 1, it's confusing. And then sigma gives us a map to C. Okay, so there's nothing else we can do. And this, because this is well defined, this proves that these symbols can't all be 0. They have to be highly non-trivial. Gives the answer to the first exercise I mentioned. Okay, so conjecture, a very difficult conjecture. Per is injective. So this is the slightly non-standard conjecture. It's the weakest possible conjecture that you can make in this theory. I'll make some comments about that in a minute. But what it says is that any relation between actual numbers, between actual period integrals, can always be lifted to the level of period matrices. So you can't have, in the period matrix I had before, you can't have a relation between periods of the first kind on elliptic curves without at the same time having the same relation between the periods of the second kind. Can't happen. That's what it's saying. So this is the weakest possible conjecture, and it's a pure transcendence conjecture. And it's not the standard conjecture. The standard conjecture, this is a massive extrapolation of the standard conjecture. But Grothendieck's period conjecture actually says something quite different. And I've always brushed this under the carpet, but I think it's worth saying because the usual conjecture, which is really Grothendieck, but then it gets attributed to, it spins on it by André, Kontsevich, Zaghi, and many others. Usual conjectures people have, not written in this language, but in my language we're talking about here, you'd have something like Norrie motives, something defined out of algebraic varieties and cycles, and that will always have a map to the ring I'm talking about here, because the ring we've described has some universal properties. It's like a universal recipient for all possible theories of motives. And then we have the period homomorphisms I've described. Here you could have Norrie motives, you could have any variant of the many constructions of motives out there. And the Grothendieck period conjecture is that this map is injective. And I think that's it's a great conjecture, but it's a very bad thing to state because it's mixing two completely different conjectures. Injectivity of this map and the injectivity of this map. This is a transcendence conjecture, is the one we've stated here, and completely elementary. And this is some kind of Hodge-type conjecture, a statement about existence of algebraic cycles. And I think it's a very bad idea to mix the two. And so this is just one part of that sort of Brilliant. Okay, so I just wanted to clarify that because there's a lot of confusion. Are there any questions so far about? Yeah. Oh, wow. Okay. Yeah, you first. I think it's like, so transcendence conjecture means pi is transcendental. Or we expect zeta 3 and zeta 5 to be linearly independent. So that statement is extremely hard, but in this setting, Motivic zeta 5, Motivic zeta 3, it's trivial to show that they're independent. And it's trivial to show that pi is transcendental in this setting. So that's what I'm saying. It automatically encodes some of the transcendence conjectures, but it encodes all of them. There was, Sergey, you had a question. Yeah, that's the very key point. Thanks. I was going to say that and I forgot to say it. So a very important point here is that in this setting, the objects come from algebraic geometry. I only consider integrals which come from polynomial equations. But the morphisms are any linear maps. Oh, I've deleted it. The morphisms can be any linear maps. That's very unusual to do this. And I think it's the right thing to do. It gives you a lot of flexibility. Then this, I think your question was about whether this is injective. In some settings, it's to do with full faithfulness of realization functors. In some settings, it's true, like mixed tape motives, we know this automatically. Here, it's a very difficult result. And if you like, you can put a pH with Hodge structures here. It will automatically be contained in that. Your question is, this map actually factors through some ring of periods where we enhance it to have some weight and Hodge filtrations. This is what I normally do because it gives you a lot more tools. Today I'm being very simple-minded, but I prefer to work with the space you mentioned, and that's automatically contained in this one. So then you're just pushing the problem is this map injective? I expect the injectivity even for vector space, absolutely. Okay, so example, Motivic 2 pi I. So I didn't explain to you how to do actual 2 pi I, so let's just do 2 pi I is integral over a loop gamma of dx over x. I have P1 here, and I have 0 infinity, and gamma will be a small loop winding around the origin. And so dx over x is a class in H1 Durham of P1 minus 0 infinity. So if you want to go back to the definitions, the complex that computes this thing is Q x 1 over x Q x 1 over x dx. And so you want the co-kernel of the differential of the formal differential d, which goes from this vector space to this vector space. So what do we want? We want, so this is a period, and gamma is a homology class on the complex points of P1 minus 0 infinity. That's just C star. Is homeomorphic to a circle. And so from this data, we now know how to turn this into a Motivic thing. We take the object H1 of P1 minus 0 infinity. This is a pair of vector spaces, Durham, Betti, and the comparison isomorphism. And then we give ourselves the data of this class. I should do Betti first. We give ourselves the data of this class in the homology, and we give ourselves the data of the class of the differential form in cohomology. And I like to call this the Lefschetz Motivic period. Lm. Okay. Sorry? Oh, y is the empty set. Yeah, sorry. Yeah, absolutely. Y. So x, you're right. So I should have said x is P1 minus 0 infinity. And there's no boundary here, so y is empty. Okay, and then we see immediately that the period of Lm equals, well, you do the integral of gamma of dx over x, and that's just 2 pi I. Yeah, I'm up. Okay, let's have 1 minute to wrap up. Just do the elliptic example and then call it a day. And I'll just say in words what this Motivic group does. Think about it. So another example, elliptic. We did it earlier. We take E smooth elliptic over Q as we'd had before, and have omega alpha M is defined to be the cohomology of the punctured elliptic curve with our chain alpha and dx over y. And etc. So you can do this with the cycle alpha, the cycle beta, and we get 4 Motivic versions of our 4 elliptic integrals. And the period alpha m omega equals integral of alpha dx over y. Okay, so we can play this game and amuse ourselves writing down Motivic versions, in other words, elements in this space of our favorite period integrals. And what this Galois group does in one short phrase is it essentially reflects the ambiguity in the Durand basis. So if we change the Durand basis, we get a different period matrix and everything transforms. That's the origin of the Galois action. Okay, so maybe just do one example before I finish. So what could happen here is you could have said, oh, well, instead of dx over x, I could have taken lambda dx over x as my form, where lambda is a non-zero rational number. That's a perfectly good basis for my cohomology. And then what would have happened is lambda m, the Lefschetz period would have become lambda Lm. That's exactly what the Motivic Galois group is doing. So if I have G in G, we'll do it. I wanted to do it today, we'll do it tomorrow. G sends the Motivic version of 2 pi I and scales it by some rational number. Okay. And that proves that this thing is transcendental immediately. Because if it were algebraic, lambda would always be constrained.